Yeah, okay. It's my great honor to be here to give the talk at the Qingtao University again. So my talk title is Recent Progress of Volume Conjectures. So I will give some comprehensive review of this area. Okay, so this is some joint work with various groups of people. That's basically. Okay. So theme of my talk is the intertwining of mathematics and physics. So the mathematics, today I would like to talk in the volume conjectures and those congruence relations, scalar relations, and cyclotomic expansions. So for the current Jones polynomial and other quantum invariants. And also even maybe they are categorifications. And this kind of mathematics is okay. So now it's okay. And it's inspired by the physics, the quantum ensemble theory, and string theory, and the larger n duality. And some possible new physics interpretation maybe can be obtained by these new discoveries in the mathematics, especially for volume conjectures for the Rashidin-Turayev invariants and the Turayev-Viro invariants, as well as the asymptotic of the quantum security symbol. Okay, so I will first review some history. So in the area of knot theory, so we want to study the knot invariant. And this is the definition for the knot and the link. So link is just several components of the knots. And so to distinguish whether two knots are equivalent or not is a big issue in the knot theory, Okay. Okay, this is some very simple examples. The N knot and the trefoil and hop link. These three, they don't have hyperbolic volume. So only this figure 8 knot. This is the simplest hyperbolic knot. It was first discovered by Riley then and Thurston later. This is we have the called the revolution of the modern hyperbolic geometry. So we want to discover some knot invariants. To find the finer and finer knot invariants is always a very interesting topic for the knot theorist. And it's also connected to other different areas like algebraic geometry and especially for Gromov-Witten theory. And also now is connected also to the modular form number theory, even the Riemann hypothesis. Some people studied that. So this is some history, the early history. So first knot invariant is by Alexander polynomial. Then Conway used the scan relation to redefine the Alexander polynomial. So this is so Conway is quite a pity. So it's two pities for him. So the first pity was 1974. So if he used the scan theory, scan relation, he can also define the Jones polynomial and Humphrey and the Kaufman polynomials. These kind of all these polynomials so can also be defined by the scan relation. And the second pity is that he passed away in because of the COVID-19. So about 2 or 3 years ago. Yeah. So he's a great mathematician, of course. Yeah. Okay. So the common factor. So all these this kind of early development, I call it early history. So they share a common factor. They can be defined by some combinatorial method. It's a very simple method. So even I think the high school students can understand. So we call it the scan relations. This kind of scan relations. So that means no matter how the knot or link be so complicated, you can always reduce this kind of calculation to less crossings, right? To less crossings. So this is a positive crossing, negative crossing, and this is the smoothing. Okay. So each time by using this kind of relation, you can reduce the number of the crossings again and again. So finally, you go to the initial condition. So the N knot is 1. Yeah. Okay, so this is then revolution always happens when the physics enters into the picture. So this is by Kirillov-Reshetikhin defined the quantum security symbol, and then Trief Trief's work then 1989. So Witten he interpreted the Jones polynomial by introducing the Chen-Simons gauge theory, and also he predicted the existence of the new invariants as well as three manifold at the root of unity. So here I would like to emphasize the root of unity is called Q1. So later we can also study the Q2, Q3, so other roots of unity. So QS is given by exponential of S pi I over R. Then 1990, so Reshetikhin-Trief, he used the quantum group theory. So to rigorously define the invariants predicted or inspired by Witten. So this is a rigorous mathematical definition. And then not only define the Q1, but also other QS. So QS, S is odd integer, and then later the Q2 can also be defined. And then Trief-Vero, they use the quantum security symbol to construct the invariants. So, and also connected to the 2 plus 1 dimensional quantum gravity. So previously the quantum security symbol and the security symbol is also related to the quantum gravity because this is a Pozzano-Reggi model. So in 1968. Okay, this is some early development of the idea of the quantum groups. The quantum groups play a very important role in mathematical physics now. So this is by Fadeev Leningrad School. So in 1981, the Coolidge and Reshetikhin, they find the first example of the quantum groups. So later is rigorously formalized by the Junfeld and Jingbo. Okay, so this is a Russian trail car. Okay, so 三套车马车. Okay, so this is in the middle is the Coolidge-Reshetikhin. So they find the first example. Then it's developed by Junfeld and Jingbo, and then here this is by Jones, the polynomial. Then influenced by Witten, Chen-Simons theory. Then rigorously defined. It's called the Reshetikhin-Trief invariance. And then this is by the Pozzano-Reggi model. It's a quantum gravity model in 1968. Quantum gravity. Then Kirillov-Reshetikhin, they defined the quantum CC symbol. Then they use Trief-Vero, they use the quantum CC symbol to define the quantum invariance. This is called the shadow theory, and this is called the surgery method. Two different kind of methods. This is the history of the three-dimensional topological quantum field theory. So it's covered here since 1980. Okay, so this is some simple definition of the quantum invariance. So this is each by the crossing, negative crossing. So it's a solution of the Yang-Box equation. Then this is you can prove this is well defined. And okay, this is anyway. So finally, by using this kind of positive crossing, negative crossing, so you can obtain a well defined quantum invariance by the R matrix. Okay, so this is some basic setups. So how can I know the time? So, oh yeah, okay. I for 5 minutes. I still have 25 minutes, right? Okay. Okay, so this is a partition. Partition is given by because the representation theory of those Hecke algebra or BMW algebra. This is all well studied by many people. So they have the standard theory. So it's by partition. So mu1 greater than mu2 until mu_k. So this means the number of the boxes. Like you have 4 boxes here, and 3 boxes, 3 boxes, and 1 boxes. The total number of boxes is 11. And the number of the rows is 4. And this is some multiplicities. So this is very important when we define for the colored Hahn-Fly invariance. This is Young tableau. Okay, so for some example, so when you consider the irreducible representation, so even you consider for an unknot, it looks quite complicated. Looks quite complicated. So this is the formula for the unknot for any irreducible representation for the colored half-life polynomial. This is called the quantum dimension. So it has a name called quantum dimension. And for each Young diagram, so we can finally, this is a one variable. So we can also have a theorem for this is for become two variables, two variable half-life, colored half-life PT invariants. Okay, so this is the building of the quantum invariance, the building. So this is the first floor, So this is type A Lie algebra, the quantum deformation of the type A Lie algebra. And this, if you use the fundamental representation, you can recover the Jones polynomial. You can recover the original half-life polynomial. And if you use type of BCD, you will always give you Kaufman polynomial. And if you consider any irreducible representation, you will get a colored Jones, colored half-life, colored Kaufman. So color means any irreducible representation. Okay. And this is only the building of the first floor. And we also have the second floor. The second floor is called categorification. This is also another very popular area. So it's by Hovanov. And this is the building of the quantum invariance. If we consider the Alexander polynomial, you can also have the categorification. This is the Higgins floor. It's developed by Oshwatz-Szabo. It's also another very important area. But this is only the building of the quantum invariance. And this is a colored Jones. Colored Jones has a hidden connection. He has a bridge to the original volume conjecture. This is proposed by Kashif in 1997. And then by Hitoshi Murakami and Jun Murakami in 2001. This is original. This is another area connecting to another area. It's called the hyperbolic geometry. And then this colored half-life, colored Kaufman. So they were connected to the open Gromov-Witten theory. This is also very important area. So it's called the LMOV, Labastida-Marinho-Ogurewafa conjecture. It was proved by Qifeng Liu and Pan. About 15 years, more than 15 years. Yeah. Okay, so this is the geometry since 1950. So the middle one is geometry analysis. The area of geometry analysis is pioneered by Yao and Xiuyuan Chen and Richard Xiong, and further developed by Hamilton and Perlman, so the middle. And then here, this is the area of the index theorem. The gang of four, I think this name is from Weinstein. So he called them gang of four, 四人帮. Okay, so the Bott, Hertzbruch, Adia, Singer et al. And index theorem. And then it's developed later, it's by the 偶像团体 Chinese F4, 戴刘麻章 is further developed. Okay. They all make, 戴刘麻章 all make a very important contribution to develop the index theorem. Okay, and then here is the hyperbolic geometry. So pioneered by Mostow, Riley, and Thurston. This is called the modern hyperbolic geometry, and further developed by Gabay and Ian Argo. So now my work, the volume conjecture, is connecting the quantum invariance, and here the hyperbolic geometry. So now I will first talk about the, we have two generalizations from the original volume conjecture. So this is the LMOV conjecture. I will quickly discuss the LMOV conjecture. LMOV conjecture is some kind of, we defined a new invariant. It's called the colored half-life polynomial. This is classical and go from the colored half-life polynomial. So it's lost a lot of good properties. So we need to recover these properties. This is called the Labastida-Marinho-Ogurewafa conjecture. So this is the classical polynomial, half-life PT polynomial. We have very good property. It's like the integrality and the symmetry and the Porter structure. But for the quantum invariance, all this nice property has been lost. It's no obvious integrality, no obvious symmetry, and no obvious Porter structures. So, and to reveal this hidden integrality, symmetry, and Porter structure for the colored half-life invariance, we require some deep ideas from physics again. So this is some early history of the Gromov-Witten theory. So in this kind of work, it's a seminal work pioneered by de Hooft. And Witten also make a huge contribution to this area. So, and Gorbankova-Waffa and Chen-Samos gauge theory finally is equivalent to the closed. This is the closed version. And we also have the open version. So they made a bridge. This is the bridge between the quantum invariance and the growth-Witten theory. So volume conjecture is the bridge between the quantum invariance and hyperbolic geometry. So this is the a bridge between the quantum invariance and the algebra geometry, especially Gromov-Witten theory. Okay. So this is some early history of the large N duality, the idea of the large N duality. So the large N duality, this is 1989 Chen-Samos gauge theory. This is the underlined is means physics, and the second word means the mathematics. So underline the sentence means physics. Okay, so this so here this left part, the left part is the quantum invariance, and the right part is the Gromov-Witten theory. So the Gromov-Witten theory here we need the open case. So it's by Cass and Melissa Liu. So they defined some for resolved conifold, Lagrange supermanifold. So this is the Oguri-Waffa. This is a very important large N duality. Is for open case. This is for closed case. Okay. So and then this is so they have the conjecture Labatida-Marino-Waffa conjecture here in the Gromov-Witten theory, open Gromov-Witten theory here. Then it's going from this bridge to the quantum invariance part. It became the LMOV conjecture. So this is finally proved by Kifeng Liu and Pan in 2007. Okay, so this is the bridge, the large N duality. Okay, so large N duality, so it's not the major topic, so I just quickly move from here. So this is but it inspired us to find more volume conjectures. So this is a starting point for more volume conjectures for the SUN invariant. So they proved that these conjectures, MOV conjecture. They discussed discovered the integrality and Porter structure and the symmetry. Okay. And this is a congruence scan relation. So congruence scan relation we have discussed. So previously we have the scan relation, right? And this quantum invariance, it's impossible to calculate it by any type of the scan relation. But we can find some congruence scan relation for these quantum invariants. This recent work, it was published by CMT just recently. Okay, so searching this kind of scan relation is one among these streams. So how to simplify the calculation after some breakthrough discovery of a new theory, the colored half-life. So calculating colored half-life is a very difficult topic. And now it also has some connection to the quantum computation. So along the way, we studied the MOV type conjecture for framed. So we discovered some good way to express those congruence scan relation. We first defined the frame that colored half-life PT invariant. Then it's a framed version for this LMOV conjecture, the framed version. And from the framed LMOV conjecture version, we discovered the so-called the congruence scan relation. Congruence. Yeah, so we need to introduce some symbol. So this is some character. This is conjugate class. This is quantum invariance. Framed conjugate class. This SL means type A. So we use the type A quantum Lie algebra. So quantum groups. Okay, so we first proof this is also have very nice properties. Has the integer coefficient and the symmetry here. And this is for the link, the colored by the same partition. Because the link we have a lot of different components. It has L components. So each component is defined, is colored by P. This P means we have P boxes, Okay, so this is the classic half-life, classic scan relation. So we can reinterpret it in this way, And then we make our new conjectures here. Okay, so this is the old scan relation. It is split into two in our new symbol. We introduce a new symbol, and this is the old classical scan relation, and then this is the congruence scan relation. These two congruence scan relation. Then we this is a positive crossing, negative crossing. This is smoothing. Okay. So then we proved several cases. Like a torus knot. So different kind of different type of torus knot, and some figure eight knot involved, and other large prime numbers. And we proved the different kind of groups for our new congruence scan relations. Okay, so this means the torus knot. This is the N knot. This is figure eight knot. Okay. And then, so from the colored half-life polynomial, we can obtain the colored Jones polynomial, colored SUN invariant, colored SUN. When SU2, colored SU2 invariant is just the colored Jones polynomial. It's just the colored Jones polynomial. So this is colored Jones, colored SUN, all can be defined in this way. And those congruence scan relation, we can also for the congruence relation for the colored Jones, we can also make it for colored Jones. And then this can recover some older result of Tangler. This is for the colored Jones, for n's colored Jones, this case colored Jones polynomial. So this is for the recover the Tangler's result. And then so why we need to care about those so many quantum invariants and this kind of congruence relation, because this congruence relation has also very tight connection with the volume conjecture. So now we see the volume conjecture. This Kashev in 1997 and Murakami in 2001. So the left hand side is a colored Jones polynomial. It's a colored Jones polynomial. So this is a knot, and this n's Jones polynomial is n plus one dimensional. And so this is root of unity e to the high I over n plus one. So this will become exponentially large. And the growth rate, the exponential growth rate is just proportional to the hyperbolic volume. So the left-hand side is defined by quantum invariance. And the right-hand side is the hyperbolic geometry. So for each, so this is the work of Riley and Thurston. So in the right-hand side. So this is, you have a hyperbolic structure. You can study the Green equations. So we can study those dihedral angle for the tetrahedron. And we can also have completeness condition. So we can calculate the volume on the right-hand side. And so this conjecture connects a very two profounded area. So by Jones, Witten, Rashitigan, and then by Riley and Thurston. For many years, the only proven case is the figure eight knot. And this is in the 1990. Then for the second case, hyperbolic case 5-2, it was proved by Ozuki and Kashev's method. So this method is by careful combination of the Poisson summation formula and the saddle point method. So he proved the case for 5-2 in 2015, and also can be applied to Kashev invariant. In 2016, 2018, so Ozuki, Yokota, and this kind of several cases. So this is again successfully applied to prove the following cases. We use the Mascom's colored Jones polynomial to prove the twist knot for P is greater than or equal to 6. So this is the first time we proved the infinite many hyperbolic knots. And a possible physics explanation of the original volume conjecture is by Gukov and also by Witten in 2003 and 2010. This is kind of we look at the twist knot. Okay, so now the twist knot, we still have some cases is still open, like a 292 K5, and this 801 10-1 are still open in the these 4 cases we cannot. Okay, then we return to the LMOV conjecture and the congruence scan relation. So from the LMOV conjecture congruence scan relation, we can define the SUN, color the SUN invariant. For color the SUN invariant, for this kind of color SUN, it looks quite complicated, but it has many ways you can define it. The difficult part is to calculate the colored SUN invariant. Colored SUN invariant, and we can also have some congruence conjecture. This kind of congruence conjecture, we can prove several cases, and it also can recover the countless result. But this interesting result, okay, 5 minutes. So we 5 minutes. Okay, no problem. Still 7 minutes. Okay. Yeah. Okay, I started a little bit late. Okay. So inspired by the congruence relation, we got to the following conjecture. So this is the SUN cyclotomic expansion. So this is proved by Habro. So you can see the gap here. This n and n plus 2. And this is a gap is enlarged, n plus small n. So this is the gap is enlarged. And all these quantum integers in this gap can be used for the volume conjecture. This is our very important observation. You see here, this is only one root of unity. But here you have many roots of unity you can use for the volume conjecture. So this is our theorem. So for the cyclotomic expansion, we proved 3 years ago by with Keifeng Liu and Shen Zhu for the double twist knot, and we make the volume conjectures. So A previously, so n equals 2, A can only equals 1. So now A can equals 1, 2, 3, n minus 1. So all these kind of roots of unity. You have a lot of choice, and we prove that this volume conjecture is true for figurative knot. Okay, so then I just said something about my work with Tianyang. So previously, so with the volume conjectures, this is a closed volume conjecture. We consider the second root of unity. So this is another direction. So with my work with Keifeng Liu and Shen Zhu, we studied for the SUN invariant. We find the volume conjecture. Now we consider different kind of root of unity. We can also have volume conjectures. So this is 3-dimensional closed orientable manifolds. So we consider the Q2 instead of Q1. So we have the volume conjectures for Rashidi trife invariant, and also the trife zero invariant. So this is we can see this is the Rashidi trife invariant is defined this way. So it's the sum of some Carry-Jones polynomial, So this result previously we numerically tested. It's already proved by a professor at RIMS. So rigorously proved. So this is the numerical test for Rashidi trife invariant. And also we can for the trife zero invariant, we also have the similar conjecture. For the trife zero invariant, so this is for the orientable, non-orientable, previously only for the not invariant. So now we have Caspar, the non-orientable Caspar manifold. So we all have volume conjectures. We numerically test this result. Okay, so the last minute. Okay. So then and some here, some I would like to say the last table. No, sorry. The last table, so we have so this is the table. So the Q1, this is no volume conjecture. No, it's a polynomial growth, called polynomial growth. So this is exponential growth. So for the second root of unity, they are all exponential growth. So this is the different kind of, we change the quantum invariance for SUN, half-life PT, and super polynomial. This Q1 and Q2. So Q1, Q2, they have a huge difference. And this huge difference, so it's corresponding maybe to a non-unitary physics theory. So previously, it's a unitary physics theory. So now it's possibly correcting to a non-unitary theory because of our new volume conjectures. The quantum integer became negative. Okay, so previously this is Q1. At Q1, we have the Witten's transformers gauge theory. We have the Rashidin tri-phase invariance, but it's polynomial growth. So now it's exponential growth. So the Rashidin tri-phase invariance, we have the new volume conjectures. Possibly it's indicator maybe a new non-unitary physics theory. Okay, so this is 19th century from linear to nonlinear. So 20th century maybe from commutative to non-commutative. 21st century maybe we can go from unitary to non-unitary. So, and happy birthday for Professor Yang.
So is there any question or comments?
I just wonder how it is related with classical volume conjecture in knot theory that complement to the hyperbolic knot has volume when related with the Kashaev invariant of knot.
Okay, so your question is, so for the original volume conjecture, it's only they use the Kashev invariant and the Carter-Jones. But now for this kind of new volume conjectures, we use the Rashidin triumph and the triumph zero. We use the in Rashidin triumph we use the surgery theory, and another triumph zero we use the 60 symbol. So your 60 symbol with Korea.
But whereas a lot of generalization of volume conjecture by Gukov and Murakami and a lot of peoples. And they are interesting in namely asymptotical behavior of some functions depending on some parameter, and the parameter go roughly to speak representation of quantum group at root of unity when order of root of unity goes to infinity.
Yeah, so I will return to their form. So you mentioned the Gukov's work. So Gukov's work, they actually they use some different parameter, but they still consider the not complement. So our volume conjecture is the first time we can consider the cusped manifold and also for the even for the closed manifold. So previously they have a lot of different kind of deformation of the volume conjectures, but they have the parameter just change the root of unity to some within some parameters there, right? So, but the volume part is still the not complement. So the advanced part of our volume conjectures, we can go from the not complement to all different other kind of hyperbolic manifolds, either cusped, either orientable, non-orientable, even totally with totally geodesic boundary. We also have volume conjectures for them. So this is the major difference.
Okay, so we thank the speaker again. Thank you.